Today, we are building a DIY safety alarm that senses physical movement and immediately triggers a loud buzzer, keeping unwanted guests away from your desk or room. Our objective is to combine a few simple electronic components with an Arduino Uno microcontroller to build a fully functional security prototype. Here is our checklist for the build. We need an Arduino Uno R3, a breadboard, an ultrasonic sensor, a piezo buzzer, a 220 ohm resistor, and a handful of jumper wires. Before we plug anything in, we need to establish a closed circuit. This is simply a continuous loop with a start and end point that allows electrons to flow freely through our devices. Once you understand how to close a circuit, you can take a loose pile of plastic and metal parts and turn them into a reactive automated machine. Let's look at the overhead workspace. Our very first step is to connect the Arduino's power supply directly to the breadboard. Take a red jumper wire and connect the 5V pin on your Arduino over to the positive power rail on the breadboard. Next, grab a black jumper wire and connect the GND, or ground, pin on the Arduino to the negative ground rail. As you do this, check this cross-section graphic. A common reason circuits fail is because wires are sitting loosely above the contacts. Push them fully into the breadboard holes to ensure they connect. By establishing these two connections, we provide the essential electrical foundation to support the rest of our closed circuit. Now we introduce the HC-SR04 ultrasonic sensor. This acts as the eyes of our security system. To place it, carefully plug its 4 metal pins directly into 4 adjacent rows on the breadboard. Take a close look at this breakdown of the sensor. The 4 pins are VCC, Trig, Echo, and GND. Route the VCC pin straight to your positive power rail and connect the GND pin down to the negative ground rail. That leaves our 2 communication pins, Trig and Echo. Route those directly to the digital input pins on the Arduino board. The Arduino will use these specific pins to constantly read distance values, bouncing sound waves off objects to monitor the physical environment. By completing this sensor loop, our system upgrades from a passive circuit to an active monitor. We have our inputs. Now we need our audible output response. For this, we use the piezo buzzer and the 220 ohm resistor. Components like this buzzer follow the rule of polarity. As this diagram shows, the long leg is positive and the short leg is negative. Place the buzzer onto the breadboard, aligning the negative short leg with your ground path. Before closing the loop, insert the 220 ohm resistor into this same path. The resistor slows down the flow of electrons, which prevents the buzzer from blowing out from too much current. Finally, connect the buzzer's positive terminal back to an available digital pin on the Arduino. Our hardware chain is complete. The system is wired to sense physical data and produce a physical response. Step away from the hardware and plug your Arduino into your computer using the USB cable. On your screen, open the provided alarm code within the Arduino software interface. Find the button highlighted here and click Upload to transfer the code from your computer directly to the microcontroller. Look at the physical Arduino board. You will see a set of tiny lights flashing rapidly. That indicates the code transfer is successful. This software upload merges our inert hardware with logic, turning our breadboard into a smart device. Time to test the system. Approach the sensor and the alarm sounds. Remove the obstacle and the alarm stops. If your alarm triggers randomly when nothing is in front of it, the sensor is likely bouncing false values off nearby clutter on your desk. To fix this, simply ensure the ultrasonic sensor has a completely clear physical line of sight. You can take these exact same input and output principles and apply them to advanced builds, like coding a digital stopwatch or building a line-following robot. Mastering these foundational components gives you the tools to prototype custom solutions for real-world problems.